Hey guys, here's a quick video for when you have cross sections, to determine volume where they're not circles. So like something like this. So here you have the region R, which is bounded by the curves listed below, is the base of a solid. So one of the things I usually I say is, this is a solid that's already been created. We're not revolving to make the solid; it's already there. And in this case, they're semicircular cross sections, and they're perpendicular to the x-axis. And these are the two curves we're using to make the region, and of course they want the volume. So let me just translate that out to the notes here. We have it was y equals x squared, it was y equals x cubed, cross sections were semicircles, and it was perpendicular to the x-axis. That's all the important information from there that we're going to need. So again, the difference is this is a solid that's already been created. If I were to just quickly graph this, you have y equals x squared is something like this, y equals x cubed is something like this, and then eventually the x cubed overtakes the x squared. Okay? So this is the region we're dealing with. And again, we're not taking this region and revolving it over the x-axis. Again, if you look carefully at the way it's worded, and this is the dead giveaway, they're telling you the region is the base of that solid perpendicular to the x-axis. You already have the solid. You're not creating the solid. So the way I always describe this, I think of it as like, for this particular one, I usually use like a banana. Pretend you took a banana and you cut it, you cut it the long way, right? And then you just slapped it down on here. Well, if you were to slice that banana, you'd actually have these little semicircles, all over. You had little ones, you'd have bigger ones, whatever it is, you'd have these little slices. Okay? So when you go to find the volume of this, you're adding up an infinite number of semicircles, these semicircle slices. So when you go to do your volume, it's really just the formula for the area of those cross sections. All the examples we did up until now, this was always pi r squared. That's why you always remembered it as pi, and then the function squared or the axis minus the function, whatever it was going to be. But it still ended up being the area of that cross section. Okay, so this sort of distance here, this x squared minus x cubed distance that we've already learned how to get, represents actually the diameter of that semicircle that's the cross section. So if I'm going to do the volume of this, it's actually going to be, it's pi r squared because it's for a circle, but it's only half of it. So it's half of pi r squared, right? But what's the radius? If this distance is x squared and this distance is x cubed, well then the diameter is x squared minus x cubed. The radius would be 1/2 of x squared minus x cubed, or x squared minus x cubed over 2. And that's how you would do one like that. Okay? So you got to read it very carefully and figure out, okay, this radius that we're always trying to get, I shouldn't write radius, this distance that we're always trying to get, I'll use little d, could represent different things. It could be the base of a rectangle. It could be the height of a rectangle. It could be the side of a square. In this case, it's the diameter of a semicircle. So your focus should always be on what formula are you using for your cross sections. Okay? So this is going to be the area of your cross sections. And again, sometimes they'll give you, sometimes they'll just hand you a formula. If you have those FRQs that I gave you, you'll see, I think there's one or two where they just say the area of the cross section is 2 sine pi, or sine x plus, 12, I don't know. And then that's what you would use here. That would be the integral, the integrand for this integral. You would just add up an infinite number of whatever they are. All right. So again, if this was a square, it would just be this times itself. There wouldn't be any 1/2 pi. It would just be x squared minus x cubed quantity squared. If it was a rectangle where the height was twice as big as the base, you'd have this times that times 2, right? You have so many options depending on what they give you, but the main thing comes down to basically this. Okay. All right. Hopefully that helps with those part D's, or whatever it is, part C, part D. And if you have any questions, be sure and let me know.